On the evening of April 6, 2026, 4 human beings slipped behind the moon. For 40 minutes, the lunar body itself, 2,160 miles of rock and iron and ancient compressed silence, sat between them and every radio signal humanity could send. No voice from Houston, no telemetry, no abort command, just the crew of Artemis 2, alone on the far side of the only world we've ever studied from the ground, orbiting at 4,600 miles above a landscape that no human eye had seen from this angle in over 50 years. Victor Glover, Navy captain, test pilot, a man who spent nearly 6 months aboard the International Space Station without losing his composure, tried to describe what he was looking at before the signal cut out. He couldn't find the words. What he said, in the moments before the blackout, was that humans had probably not evolved to see what he was seeing. That's an unusual thing for a test pilot to say. This documentary is not about the Artemis 2 mission. It's about what Glover was looking at, and more specifically, about why what he was looking at has forced scientists to ask a question that the entire history of lunar science managed to avoid asking until now. For the next hour, we're going to examine the evidence that explains why the moon's far side is not just different from the near side, but different in ways that directly challenge the model we built to explain how the moon, and by extension, everything else in the solar system, came to be. We're going to look at the data, all of it, what it confirms, what it contradicts, and what it means that we built our understanding of lunar asymmetry and the planetary models that depend on it, almost entirely on observations of one half of one world. The full picture, it turns out, looks nothing like the half we knew. Here is the foundation of everything that follows. Between 1969 and 1972, NASA landed 12 human beings on the moon, 6 missions, 6 landing sites, a total of 382 kilograms of rock and regolith brought back to Earth. Those samples transformed our understanding of the solar system. They gave us the first physical evidence of how a rocky world forms, cools, and evolves over billions of years. They are, even today, among the most scientifically valuable materials ever retrieved by a human expedition. Every single landing site was on the near side. This was not an oversight, and it wasn't a failure of ambition. It was a physical constraint. The near side of the moon faces Earth. Direct radio communication, the lifeline that mission control requires, only works on the near side. To land on the far side, you'd need a relay satellite permanently positioned in a halo orbit beyond the moon to maintain communication. In 1969, that technology didn't exist. It still didn't exist, in practical form, until China flew one in 2018. So the Apollo program landed where it could, studied what it could reach, and returned with a data set that was genuinely extraordinary, and geographically limited to roughly half of the moon's surface. What that near side showed us was remarkable. Vast flat plains of dark volcanic basalt, what geologists call maria, covering about 31% of the surface. Ancient lava flows that had poured into massive craters billions of years ago and cooled into smooth, dark seas visible to the naked eye from Earth. The rock samples told us when this happened, most of the major volcanic activity on the near side took place between 3 and 4 billion years ago. The moon formed hot, geologically active, and gradually cooled into the apparently quiet body we see today. From orbital imagery, we knew the far side was different. The Luna 3 probe photographed it in 1959. The Apollo 8 crew flew over portions of it in 1968. By the 1990s, orbiting spacecraft had mapped it in reasonable detail. What they showed was a surface dominated almost entirely by impact craters. Ancient, densely packed, with almost none of the dark volcanic plains that define the near side. Less than 1% of the far side is covered in basaltic maria. The crust is roughly 50 kilometers thicker. The terrain is rougher, older, more heavily battered, If this kind of deep investigation into the science behind our assumptions is why you're here, the like button helps this reach more people who'd want to spend an hour on this. Scientists had models for why this asymmetry existed. The leading theory involved radioactive heat-generating elements, potassium, thorium, uranium, concentrated on the near side in a geochemical province called the Procellarum creep terrain. The idea was that this concentration of radioactive material kept the near side mantle warm enough to sustain volcanic eruptions long after the far side had gone cold and quiet. It was a reasonable model. It fit the available orbital data. It explained the broad outlines of what we could observe. The problem, which we are about to examine in full, is that the model was built almost entirely on what we could reach. And what we couldn't reach, the far side, the actual physical material of the moon's hidden hemisphere, was assigned properties by inference, by assumption, by the extrapolation of data from one side of a world to the other. Think about what that means for a moment. We built a model of the moon's interior, its thermal history, its volcanic evolution, and its chemical composition. A model that then informed how we think about every rocky body in the solar system, primarily from samples collected in one geographically constrained region on one hemisphere of one world. That's not a criticism of the scientists who built it. It was the best available data. It produced genuinely important science. But there is a difference between a model built on the best available data and a model built on complete data. And in 2024, for the first time in the history of lunar science, we got physical material from the other side. What the laboratory found in those samples is why this documentary exists. But before we get there, we need to spend time with the most extreme feature of the far side itself. Because what sits on the far side's southern hemisphere is not just an anomaly. It may be the key to understanding why the two sides of the moon are so fundamentally different. And buried beneath it is something that, according to the data, should not still be there. The South Pole-Aitken Basin is the largest confirmed impact crater in the solar system. That sentence is technically accurate. It is also insufficient. The numbers that describe this feature require comparison to make them land correctly. So here is one. If you place the South Pole-Aitken Basin on a map of the continental United States, it would cover everything from New Mexico to Virginia. End to end. All of it. That's the diameter. Roughly 2,500 kilometers across, and it plunges downward at its deepest point, approximately 13 kilometers below the surrounding terrain. The mountains along its rim reach elevations of 8,500 meters. Those are among the tallest peaks on the moon. The basin was formed by an impact event that is estimated to have released energy greater than that of 1 trillion atomic bombs. It happened approximately 4 billion years ago, give or take a few hundred million, when a body, probably somewhere between 170 and 320 kilometers in diameter, struck the moon's southern hemisphere with enough force to gouge out a hole large enough to swallow a continent. The South Pole-Aitken Basin sits almost entirely on the far side of the moon. The Apollo missions never went near it. Its floor, its walls, the material excavated by the impact and redistributed across the southern hemisphere. None of this was ever physically sampled before 2019, when China's Chang'e 4 rover became the first spacecraft to land inside it. And no sample from its floor was ever returned to Earth before June 2024. But the most significant thing about the South Pole-Aitken Basin is not what's on its surface, it's what's underneath it. In 2019, a team led by planetary geophysicist Peter James at Baylor University combined gravity data from NASA's GRAIL mission with topographic data from the Lunar Reconnaissance Orbiter. They were looking for anomalies in the moon's gravitational field, places where the gravity was measurably stronger or weaker than the surrounding terrain would predict. What they found beneath the floor of the South Pole-Aitken Basin was not what anyone expected to find. There is a mass anomaly sitting at least 300 kilometers below the surface of the basin. a concentrated region of dense material with a total estimated mass of at minimum 2.18 quintillion kilograms. James described it, in the language of a scientific paper, which is not language given to dramatization, as roughly equivalent to burying a pile of metal 5 times larger than the big island of Hawaii deep underground. The anomaly is heavy enough that its gravitational pull drags the entire floor of the basin downward by more than half a mile. The most likely explanation, according to James and his team, is that this mass is the metallic core of the asteroid that created the basin in the first place. The impactor struck the moon at high velocity, punched through the crust, and its dense metallic interior sank into the lunar mantle, where it has remained, undisturbed, for 4 billion years. The object that created the largest impact crater in the solar system is still inside the moon. No model predicted it would still be there. Think about what that requires. Over 4 billion years, through countless subsequent impacts, through the gradual cooling of the lunar interior, through whatever convective processes operated in the early moon's mantle, this object never moved, never dispersed, never became part of the surrounding rock in any way the gravity data can't still detect. Like a bullet fragment that a body encased rather than expelled, it's still there, pulling at the crust above it, warping the gravitational field, sitting 300 kilometers below a surface that has been photographed and mapped and studied for 60 years without anyone going to get it. That mass anomaly is Loop A of this investigation. We've named it. We've measured it. We have a candidate explanation. What we don't have is confirmation. The only way to confirm what that object actually is would be to drill 300 kilometers into the lunar mantle and retrieve a sample. We haven't done that. We can't do that. Not yet. Hold on to that, because the anomaly beneath the South Pole-Aitken Basin becomes more significant in the context of what the Chang'e 6 samples found in 2024. Those two datasets, read together, suggest something about the far side's interior that neither one could establish on its own. But that's not the only thing the basin is hiding. In 2023, researchers published findings on a thermal anomaly buried beneath the far side surface, a region approximately 50 kilometers wide that registers roughly 10 degrees Celsius warmer than everything around it. The likely source, according to that analysis, is a massive buried block of granite. Granite is common on Earth. It is almost unheard of on the moon, because granite requires two things the moon is not supposed to have: liquid water and plate tectonics. The leading hypothesis is that this granite is the remnant of a volcano that went dormant approximately 3.5 billion years ago, its residual magma still radiating faint heat. The lead scientist on that study noted that the finding looks far more like what we see on Earth than anyone had thought possible on the moon. And that description, looking more like Earth, is precisely what makes it so difficult to fit into the standard model. Two anomalies beneath the far side's surface, both confirmed by independent data, neither fully explained, and we haven't yet looked at the rocks. We've established the foundation. The near side gave us a model. The far side, in orbital data alone, showed us something the model didn't predict: a buried mass that's been sitting undisturbed for 4 billion years, and a heat source that shouldn't be there at all. But orbital data has limits. Gravity measurements and thermal readings tell you something is there. They don't tell you what it is made of, how it got there, or what it means for the processes that shaped the entire moon. For that, you need rocks. In June 2024, a Chinese spacecraft returned 1,135 grams of physical material from the far side of the moon, from inside the South Pole-Aitken Basin itself. For the first time in the history of lunar science, researchers had actual physical samples from the moon's hidden hemisphere sitting in a laboratory. And when they ran the analysis, a full deep dive into composition, mineral structure, isotope ratios, water content, and magnetic signature, what they found contradicted the standard model in not one place, but 4. Chapter 3 is where the data meets the model. and the data doesn't agree. China's Chang'e 6 mission launched on May 3, 2024. It traveled to the far side of the Moon, landed inside the South Pole-Aitken Basin, collected rock and soil from the surface, and returned its samples to Earth on June 25, 2024. It was the first soft landing on the far side ever to return material to Earth. It required a relay satellite, the Quintillion, permanently parked in a halo orbit beyond the Moon, because you cannot communicate directly with the far side from Earth. Every command, every data packet, every instrument reading had to bounce off a satellite specifically positioned to bridge that gap. The samples themselves looked different immediately. Researchers who had handled Apollo and Chang'e 5 samples, near-side material, noted that the Chang'e 6 soil was lighter in color, more cohesive, physically unlike the near-side material even before laboratory analysis began. Chang'e 5 samples are nearly jet black and collapse readily, like dry sand. The Chang'e 6 samples are lighter, almost whitish in places, and hold their shape on steep slopes. That visual difference was the first signal that whatever process shaped the far side surface was genuinely distinct from what shaped the near side. Then the laboratory results came back. 4 separate research teams affiliated with the Chinese Academy of Sciences, Nanjing University, and other institutions published their findings in 4 concurrent articles in the journal Nature in July 2025. What they described was not a refinement of the existing model. It was a series of direct contradictions. Contradiction 1: water content. The standard model of lunar formation assumes that after the Moon's magma ocean cooled and solidified, the distribution of volatile elements, including water, was broadly similar across the interior. There was some expectation of variation, but the overall picture was one of a gradually desiccated Moon, with water driven off by the heat of formation. The far side mantle was expected to be roughly comparable to the near side mantle in terms of water content. What the Chang'e 6 samples showed was something else entirely. The far side basalt samples were significantly drier than any near side material previously analyzed. The researchers found that the far side mantle source region was, in their words, ultra-depleted in volatile elements including water. Not slightly different, not marginally drier. The far side mantle appears to be fundamentally, chemically distinct from the near side mantle, in a way that the model of a single, cooling lunar interior cannot easily account for. The correction should have brought the water content closer to near side values. It moved further away. This is the moment where the investigation changes direction, because a single anomaly in a single dataset is a puzzle. 4 independent anomalies in 4 separate analyses of the same samples is a pattern. And the pattern the Chang'e 6 data describes is not consistent with a Moon that cooled uniformly from a single common interior. Contradiction 2: volcanic timing. The standard model predicted that far-side volcanic activity ended significantly earlier than near-side volcanism, consistent with the near side's radioactive heat-producing elements sustaining geological activity longer. What the Chang'e 6 analysis found was evidence of volcanic activity on the far side at 2.8 billion years old, more recent than several models had allowed, and linked to what the researchers described as an ultra-depleted mantle source that had been exhausted in a way inconsistent with simple cooling. The volcanic history of the far side doesn't follow the curve the model predicts. Contradiction 3: the magnetic signature. Researchers analyzing the physical properties of the Chang'e 6 basalt found evidence of an ancient magnetic field recorded in the rock. A dynamo signature that was, unexpectedly, stronger than what near-side rocks of comparable age had recorded. This matters because the Moon's global magnetic field disappeared billions of years ago. Near-side samples had shown us what that fading dynamo looked like. The far-side samples are showing us a different version of the same event, and the 2 versions don't match. The magnetic anomaly that the Artemis 2 crew photographed from orbit, the bright swirling pattern of Reiner gamma, a surface marking associated with a localized magnetic field, is not the only place the far side holds a record of something the near side doesn't fully explain. The rock itself carries the signature of a dynamo that may have operated differently on each hemisphere. And contradiction 4, the one that may matter most for the broader model, is the isotope ratio. Researchers measured the ratio of potassium-41 to potassium-39 in the Chang'e 6 samples and found it significantly elevated compared to near-side material. According to study leader Heng Qi-Tian, this isotope signature is a direct relic of the South Pole-Aitken impact. The collision was so violent that it vaporized large quantities of moderately volatile elements from the far side crust and mantle, including potassium, and drove them off into space. The far side, geochemically, bears the permanent scar of that impact in every rock it produces. The near side does not. Two independent data sources, gravity measurements and laboratory chemistry. Same region of the moon, different kinds of evidence, and they agree on the same conclusion. The near side and the far side of the moon are not just topographically different. They are chemically, thermally, magnetically, and hydrologically distinct in ways that the current model cannot fully account for. But here is where it gets genuinely difficult to explain, because the implications of these four contradictions don't stop at the moon. If the standard lunar formation model was built on data from only one of two geochemically distinct hemispheres, the question isn't just what we got wrong about the moon. The question is what else we built on the same kind of incomplete foundation. Let's be precise about what the model actually is, because this matters for understanding exactly what the evidence is challenging. The giant impact hypothesis is the scientific consensus on the moon's origin. Approximately 4.5 billion years ago, a Mars-sized body, scientists call it Theia, collided with the early Earth. The energy of that collision was sufficient to vaporize significant portions of both bodies. The resulting debris, a mixture of Earth material and Theia material, gradually coalesced in orbit and became the moon. The moon formed as a ball of molten rock, a magma ocean that slowly cooled and differentiated over hundreds of millions of years. Denser minerals sank, lighter minerals floated to form the crust. The last magma to crystallize formed a layer rich in incompatible elements, potassium, rare earth elements, phosphorus, the material geologists call creep. The creep material is almost entirely concentrated on the near side of the moon, in the Procellarum creep terrain. This is the geochemical province that contains about 60% of all the basaltic volcanic deposits on the entire moon. It is the epicenter of the lunar asymmetry. The far side has almost none of it, and the model's explanation for why this concentration exists on the near side, and not the far side, is the part that the Chang'e 6 data is now complicating. The leading hypothesis is that the South Pole-Aitken impact triggered the asymmetry. The collision, occurring approximately 4.25 billion years ago, sent a massive thermal plume through the lunar interior, a shock wave of heat that destabilized the pattern of convection in the solidifying magma ocean and drove the creep material toward the near side. In this model, the moon's two-faced nature is a direct consequence of a single catastrophic event. It's a compelling explanation, and the Chang'e 6 isotope data on potassium supports part of it. The impact clearly drove volatile elements off the far side in ways the near side didn't experience. But the data also shows four things the model didn't predict: the magnitude of the water asymmetry, the timing and character of far side volcanism, the strength of the ancient far side magnetic dynamo signature, and the chemical depletion profile of the far side mantle. The model accounts for some of what the data shows. It doesn't account for all of it. And in science, a model that accounts for some of the evidence while contradicting other parts of the same evidence is a model under pressure. The model said, uniform cooling. The data says, asymmetric water. The model said, no volcanic activity after 3 billion years on the far side. The data says, 2.8 billion years old. On the far side. After the model says it stopped, the model said, comparable magnetic signatures across both hemispheres in rocks of equivalent age. The data says, the far side dynamo left a stronger imprint than near side rocks predict. The model said, the mantle source regions are broadly similar. The data says, ultra-depleted, with a depletion profile that simple convection alone doesn't explain. The researchers who published these findings were careful, as scientists are, to state that no single explanation has been ruled out, and that the data from a limited sample set, however significant, requires further study. Wu Fuyuan of the Chinese Academy of Sciences, one of the lead researchers on the project, described the SPA basin as having exactly the kind of record we needed to clarify the compositional differences between the near and far sides. That clarification, he noted, is still incomplete. The samples represent the beginning of an answer, not the answer itself. But here is what the evidence, taken as a whole, does establish. The Moon's two hemispheres are distinct enough that the data from one hemisphere is not a reliable proxy for the other, which means every model we built by measuring one side and extrapolating to the whole was working with half the information it needed. And the Moon is not the only place we've done that. When we study Mars, we study it from orbital data and from the handful of landing sites we've reached, all of them chosen for accessibility and scientific interest, not for hemispheric representativeness. When we build models of how Mercury or Vesta or any rocky body in the solar system formed and evolved, we build them from the data we have, which is always, by necessity, incomplete. The question the lunar asymmetry is forcing us to ask is not just about the Moon, it's about the methodology. What happens when the data we've been treating as representative turns out to be a sample from one side of a two-sided story? What remains open, and this is loop B of this investigation, is whether the Moon is an exceptional case, or whether hemispheric asymmetry of this kind is a predictable feature of planetary-scale impacts that we've been systematically underestimating because our sampling strategy couldn't detect it. That question reaches into every planetary model in the solar system, and Chapter 5 is where we look at exactly how far it reaches. We've now looked at two independent data sets on the lunar asymmetry. The gravity data confirms something anomalous and massive buried in the far side mantle. The Chang'e 6 laboratory analysis confirms 4 simultaneous contradictions between the far side samples and the standard model's predictions. Both datasets are real. Both are published in peer-reviewed journals. Neither has a complete official explanation. What we haven't yet examined is what it means, not for the Moon, but for the entire framework of planetary science that the Moon was used to build. Not what the data shows, what it implies. Everything established in the last 35 minutes becomes the foundation for the question that Chapter 5 examines. If we built the model wrong, if the Moon we studied was never a representative sample of the Moon that exists, what else in our understanding of the solar system was built on the same kind of partial view? The data in the next chapter is the reason this documentary exists. There is a version of this documentary that stops here. It presents the anomalies, notes they are unresolved, acknowledges the model is under pressure, and closes with a responsible summary of the open questions. That would be an accurate account of the science. It would also miss the deeper implication, the one that makes this investigation genuinely significant, rather than merely interesting. So let's go there. The Moon is the most studied object in the solar system outside of Earth itself. We have been observing it for thousands of years. We have 6 surface landings, dozens of orbital missions, 382 kilograms of physical samples, and decades of laboratory analysis. No other body beyond Earth has received anything close to this level of scientific attention. The moon is our baseline. It is the object against which we calibrate our models of how rocky worlds form, evolve, and differentiate. And yet, all 6 of those landings were on the near side. All 382 kilograms of samples were near-side material. Every surface measurement, every soil analysis, every seismometer reading from the Apollo era, near side. The orbital data that covered both hemispheres gave us topology and gravity gradients. It didn't give us chemistry. It didn't give us isotope ratios. It didn't give us water content or magnetic signatures or the detailed record of volcanic timing that physical samples provide. We built the model of the moon from the near side, and then we used that model to build models of other worlds. The giant impact hypothesis, our best account of how the Earth-Moon system formed, was calibrated largely against near-side samples. The timescales for planetary differentiation, the behavior of volatile elements during magma ocean cooling, the relationship between impact events and interior chemical evolution, all of this was developed against a dataset that, as we now know, represented only the geochemically dominant hemisphere of the world being studied. We're talking about a rock the size of the Hawaiian Islands, buried under hundreds of kilometers of lunar crust. It's closer to the surface than you are to the center of the Earth right now, sitting where you are. That object, that buried mass, confirmed by gravity data, unconfirmed in composition, has been influencing the local gravitational field and possibly the convective behavior of the lunar interior for 4 billion years. We didn't know it was there until 2019, and we still don't know what it's made of. I want to be careful here, because the honest answer, and I've sat with this material for a long time, is that I don't think we have a framework yet capable of holding all of this at once. The water asymmetry, the magnetic asymmetry, the volcanic timing, the buried mass, the granite that shouldn't exist, the thermal anomaly that's still radiating. Each of those findings has a candidate explanation. What we don't have is a single coherent model that accounts for all of them simultaneously without introducing new questions that the model can't yet answer. And I'm not sure we should pretend otherwise. Here is what makes this significant beyond the moon itself. The methodology we use to study the moon, land where you can reach, sample what's accessible, build the global model from the available data, is the same methodology we use everywhere. It's the only methodology we have. We don't get to choose where to land on Mars based on geochemical representativeness. We land where the terrain allows it, where the science is richest, where the mission can survive. We sample what we can reach and infer what we can't. The lunar asymmetry is a direct demonstration of what that methodology can miss. We studied the moon's near side intensively and built a model. The model was good enough to explain most of what we observed. The far side, the part we couldn't physically sample, was assigned properties by extrapolation. Those properties, as the Chang'e 6 data now shows, were wrong in at least 4 measurable ways. Now ask yourself, where else have we done this? In the context of Mars, we have surface missions, but all of them landed in the northern hemisphere or near the equator. Mars has its own hemispheric asymmetry. The northern lowlands and southern highlands are dramatically different in age and composition in ways that remain only partially explained. We have very little physical sample data from Mars. What we have comes from meteorites that may or may not be representative of the planet's interior. In the context of planetary formation models generally, the giant impact hypothesis is the consensus, but it was built in part on lunar samples. If those samples were not representative of the moon as a whole, if the far side data tells a different story about how the moon's interior evolved, then the model it helped build may need revision in ways we can't yet fully specify. Earlier in this documentary, I flagged the secondary magnetic signal recorded in the Chang'e 6 basalt as a detail to hold on to. Here is where it pays off. The far-side dynamo signature is stronger than near-side samples of equivalent age. This means the Moon's magnetic field, when it existed, was not uniform across both hemispheres. The near side and the far side recorded the same event differently. That discrepancy is not just about the Moon's past. It's about what we assumed was uniform that wasn't. And if the Moon's magnetic history is more complex than the near-side samples suggested, then every model that used those samples to calibrate the timing and strength of early planetary magnetic fields is working with a partial record. We built the model of a world from one side of that world, and the other side has been waiting 4 billion years for someone to go and look at it properly. As of this recording, that project has only just begun. The evidence taken as a whole points toward two possibilities. Either the standard model of lunar formation is fundamentally incomplete in ways that will require significant revision, or the Moon's internal evolution was far more complex than a single magma ocean cooling uniformly from both hemispheres would predict. There is no comfortable middle ground between those two positions. Both of them require us to revisit assumptions that underpin not just our understanding of the Moon, but our understanding of how rocky worlds in general behave after a catastrophic impact. That is the full weight of what the far side data is telling us. And the investigation is not over. It's just started. Let's take inventory. Because after an hour with this material, the viewer who has been paying attention deserves a clear, honest accounting of what the evidence actually establishes, and what it doesn't. What the data confirms: the near side and the far side of the Moon are geochemically, topographically, thermally, and magnetically distinct. This is no longer inference or hypothesis. It is directly established by physical samples analyzed in multiple independent laboratories. The asymmetry is real. The differences are measurable. The magnitude of those differences, particularly on water content and mantle depletion, is larger than the standard model predicted. What the data confirms: something massive and dense is buried approximately 300 kilometers below the floor of the South Pole-Aitken Basin. The gravity data from the Grail mission establishes this. The estimated mass is 2.18 quintillion kilograms. The most plausible explanation, the metallic core of the impactor that created the basin, has not been confirmed or refuted by any direct measurement because we cannot yet directly sample the lunar mantle at that depth. What the data confirms: the Artemis 2 mission in April 2026 provided the first human visual and photographic observations of the far side at close range in over 50 years. And the photographs, most of which had not yet been fully analyzed as of this recording, will provide the first human-quality observational data on far-side terrain features that no robotic camera has captured at equivalent resolution. As of this recording, no published model fully accounts for all 4 of the contradictions the Chang'e 6 samples revealed. What remains open: the mechanism that concentrated creep material on the near side and produced the far side's ultra-depleted mantle is still debated. The South Pole-Aitken impact hypothesis accounts for part of the evidence. It doesn't account for all of it. Whether additional impacts, different timing, or some aspect of early lunar convection that no current model captures is responsible for the full asymmetry, we don't know. What remains open: the true nature of the buried mass anomaly. The metallic core hypothesis is the leading candidate. It is not confirmed. The data that would confirm it would require drilling 300 kilometers into the lunar mantle, a mission that no space agency has currently proposed in executable form. What remains open: the lava tubes. Radar data and high-resolution imagery suggest the Moon harbors underground tunnel networks formed by ancient lava flows, entrance pits visible from orbit, tunnels that could, in some estimates, be large enough to contain structures the size of city blocks. The Artemis 2 crew observed terrain above some of these suspected tube systems. Their photographs may help constrain where the entrances are. What's inside them? Whether preserved volcanic deposits, trapped gases, pristine material that has never been exposed to space weathering is entirely unknown. They are sealed. We haven't opened one. And there's something else the far side offers that we haven't discussed, and that belongs in any honest accounting of what we know and what we're losing by not going there faster. The far side of the moon is permanently shielded from Earth's electromagnetic noise. Every cell tower, every broadcast signal, every Wi-Fi router, every radar installation, all of it is blocked by 3,400 kilometers of solid rock. For radio astronomers, the far side is the quietest listening post in the inner solar system. Telescopes placed there could detect radio frequencies below 30 megahertz that Earth's own ionosphere blocks completely. Frequencies that carry information about the universe's first few 100 million years, the period before the first stars formed, when the cosmos was mostly hydrogen and darkness, and the gradual gravitational assembly of the structures that would eventually become galaxies. We have never heard that signal. Not once. Because every instrument we've built capable of detecting it has been surrounded by our own noise. The far side could change that. Multiple space agencies have proposed placing a radio observatory on the far side. None has been built yet. Victor Glover said, in the moments before Artemis II's blackout, that what he was seeing was beyond what humans had evolved to perceive. I told you at the beginning of this documentary that we'd return to that statement. Here's what it means, I think, read against everything we've examined today. When you build a model of something, you build it from what you can reach. You calibrate it against what you can measure. You extend it, by inference, to what you can't. That's not a flaw in the scientific method. It is the scientific method, operating within the constraints of available technology. The Apollo scientists didn't fail to sample the far side. They couldn't. The instruments to do it safely didn't exist. What Glover saw, and what his instincts recognized before his training could process it, was a landscape that his mental model of the moon had never prepared him for. Because his mental model, like everyone's, was built from the near side. The far side was there in the photographs, in the orbital data, in the mission briefings. But it wasn't in the part of his understanding that had been built by half a century of science talking about the moon as if it were one coherent thing. The data is real. The anomalies are confirmed, the questions are open. If you've spent this hour sitting with the weight of what it means, that the most studied body in the solar system had a hidden half, and the hidden half tells a different story, that's the appropriate response. The scientists working through the Chang'e 6 samples feel the same weight. The researchers modeling the buried mass anomaly feel the same weight. The question is genuinely unresolved. And the unresolved part is not a failure of science. It's science doing exactly what it's supposed to do, following the evidence into territory the model didn't predict. We open this documentary with a question about a test pilot who couldn't describe what he was looking at. An hour later, that question is larger, not smaller. The far side of the moon is not finished yielding its evidence. The Artemis II photographs haven't been fully analyzed yet. The Chang'e 6 samples are still being worked through. Additional findings are expected in the coming years. The Artemis program has future missions planned that will land humans on the lunar surface for the first time since 1972, in terrain close to the far side's southern boundary. China has announced plans for crewed lunar landings this decade. Both programs have scientific objectives that specifically target the questions the Chang'e 6 data raised. The next major dataset, physical samples from a second far-side location, ideally from a site geochemically distinct from the Chang'e 6 landing zone, would either confirm the pattern these four contradictions suggest or complicate it in ways we can't currently predict. That mission doesn't exist yet. When it does, everything we've examined today will either be validated, revised, or overturned. That's the nature of this work. The moon doesn't wait for our models to catch up before showing us something new. It's been out there for 4 billion years, holding its evidence on both sides. While we looked at one, we have finally started looking at the other. When this documentary began, I said that Victor Glover's description of the far side, beyond what humans had evolved to see, was an unusual thing for a test pilot to say, and I said the documentary was about what he was looking at. We now have a clearer picture of what that was. He was looking at a landscape that 4 billion years of impact history had preserved in a form the near side long ago erased under blankets of lava. He was looking at the floor of the largest crater in the solar system, and above a buried mass that may be the remnant of the object that created it. He was looking at terrain above a heat source that's still active, above tunnel systems that have never been entered, above a mantle that is geochemically and hydrologically distinct from everything every Apollo mission ever sampled. He was looking at the half of the moon that the model wasn't built on. Every map of the moon that science has ever drawn was drawn from the near side. Not because scientists were incurious about the far side, but because a map can only include what the cartographer can reach. The far side was always there in the orbital images, always there in the gravity data, always there in the photographs from robotic missions. But a map drawn from a distance is not the same as material retrieved from the ground. And what the ground reveals, when you finally get to it, is not always what the map predicted. The lunar asymmetry, that persistent, confirmed, still not fully explained difference between the moon's two faces, is, in the end, a reminder about the nature of models. A model built on the best available data is still a model built on incomplete data. It will be right about many things. It will be wrong about others. And the things it's wrong about tend to be the ones hiding in the parts of the territory the map didn't cover. This is what makes the far side matter beyond the moon itself. Not the specific anomalies, the buried mass, the water asymmetry, the granite, the magnetic discrepancy, though each of those is genuinely significant. What matters is the principle. We studied the most accessible part of the closest world we could reach. We built our models accordingly. And when we finally got to the part we couldn't reach before, the actual far side lunar asymmetry, confirmed in physical samples, it told us the model needed revision in 4 simultaneous ways. That's not a failure of science. That's science working as designed. But it is a prompt. It is a prompt to ask, of every model we've built in every domain where our sampling has been constrained by what we could reach, what is the far side of this question? What is the half we haven't gotten samples from yet? The most unsettling part of this story is not what we found on the far side. It's that we spent 50 years building the model before we went to get it. Because in the end, the universe doesn't organize itself around the hemisphere we happen to be able to reach first. If this kind of investigation, one topic, 1 hour, the full picture as far as current data goes, is what you want more of, the subscribe button puts the next one in your feed when it drops. If something in this hour landed differently than you expected, leave 1 word in the comments, confirmed or unexplained. I read everyone. The far side of the moon has been waiting 4 billion years for someone to go look at it properly. We've only just started.